Hi everyone, and welcome to our video on converting polar equations to rectangular equations. Now, in the previous video, we went the opposite way, rectangular to polar, and we just had to use, and we wrote them all out, we just had to use these two. Well, if we're going from polar to rectangular, we would be pretty much using all four different scenarios. Okay, and that's written here. So we're using all four. We're trying our best to rewrite it the best way we can. And I would say there's really not any special formula you want to go with first, unlike these. So this is nice. So rectangular to polar, instantly you're just plugging stuff in and simplifying. Here we might happen to manipulate things. All right, so in this first one, convert the following polar equations to rectangular form. All right, well, I have an r equals 9 all by itself. Well, looking at those equations, so let me even write them here. So I have them as a list vertically. So or x is r cosine theta, y is r sine theta. Here's where so I've written this with square roots, but here it might be better to leave it like that. And then our tangent of theta, probably better to leave it like that. Okay, so we don't have to do that. We can use these as well, and actually these might be better. Okay, so if I solve for r, I have that, and if I solve for theta, I have that. Well, let's try just using these. I think this could work better than my plan that I was about to do. Let's just use these. Okay, so if we have polar to rectangular, let's plug these in. So for instance, they're saying this r would be plus or minus the square root of x squared plus y squared, and then 9 is still over there to the right. Well, so this is why this equation isn't the best right now, because this wouldn't finalize it. What they would say, though, is we shouldn't have a plus and minus, and it's not looking good to have a square root either. Well, to get rid of the square root and the plus and minus, we should square both sides. So then squaring a plus and minus, so that square goes to the plus and minus, and it does the square root. Well, what it's saying is a positive number getting squared would stay positive. A negative number getting squared would also become positive. So that means I'd no longer have plus minus, and then the square root and the square would just cancel. So we'd have x squared plus y squared equals 9 squared is 81. There we go. Now this is a special formula. So often we try to get y by itself, but on this problem we wouldn't. This is the equation of a circle. So this is a circle with center 0, 0, and the radius would be 9, which is exactly what this equation is saying. They're saying you have a circle with radius equal to 9. Okay, and we'll get into graphing more soon. But it is showing you can convert between the others to get these graphs very soon. Okay, number two. Number two, we have theta equals 2 pi thirds. All right, well, if I have theta equals 2 pi thirds, I can say, kind of similar to the last one, I have theta could just be tangent inverse of y over x, and then on the right, I have just random 2 pi thirds. Okay, so again, this is where it doesn't work out maybe the best. I don't want that tangent inverse anymore, but what I can do is do tangent to both sides. Okay, so tangent and tangent inverse would cancel, and I would have y over x, and then tangent of 2 pi thirds we can do. So tangent of 2 pi thirds is going to give us a negative radical 3. So we have y over x is negative radical 3. Now in this problem, since it's easy to solve for y, we can just multiply the left and right side by x, and we would see that we're going to get y equals negative radical 3 times x. Okay, so what we do have is a line in this scenario. But again, we'll be graphing these in the next batch of videos. So let's just stick to this conversion. So if we can solve for y easily, or if we recognize that it's not a special equation like the first one, then we should try to solve for y. Okay, so let's see these. All right, so I plug those in this time. Here's where, okay, so I said first, probably all 4 is what we might want to be thinking about. And then I changed my tune on these last 2 problems to show it. Well, if we tried plugging those in, so if I did say r is plus or minus the square root of x squared plus y squared equals 16, oops, and I put the parenthesis in the wrong spot. And then if I say, oh, so I'm just changing those. And if I said 16 sine of tangent inverse of y over x, like that, then we might have a problem in this expression. We might have made things harder than what they really could be. Okay, so this will work eventually. I mean, the plus minus they're not going to like, so they're going to have to square it. This scenario, though, is telling us we would need a triangle with y over x, and then we can solve for the hypotenuse and eventually evaluate all of this. Okay, so we have a composition with a trig function. All right, however, instead, okay, so I'm just rewriting the main thing. I'm going to say maybe we should stop here. Again, if you want to keep going with it, you'll see that we'll get the same thing eventually that I'm about to get. But this is where now I think it is better to look at all 4. Because if I have a sine function, the main thing that I want with it is r. So I'm saying I should have an r right there with the sine. And so that's what I'm going to put. I'm going to say I should have an r right here. And so what I'm doing is multiplying this side by r, which means I would also need to multiply the other side by r. Okay, so if I see a sine function without an r on it, I'm making it to where I have one. So that way I can just change it to y. Okay, so then we can change this into r squared. So r times r is r squared. And then 16r sine theta, just rewriting it. And then we can say, well, this here is the same thing as just y. And then 16 still there. And then r squared in our equations is x squared plus y squared. It's one of those. So we could just say, well, there's x squared plus y squared right there. Now, this could be fine for a final answer. But they might say, well, you see, you have an x squared and y squared, so shouldn't that be a circle eventually? But I have another y on the other side. So what we would need to do, or possibly need to do, is subtract the 16y over. Again, I'm leaving some space because they might want us to complete the square. Okay, so and I think this is mostly a waste of time for us in these problems, but just to be safe, let's complete the square on this. Completing the square would mean I need to, let's go ahead and put it in purple. Oop, I pushed a button on my pen and it freaked out. Okay, so complete the square is to take this value that's attached to the linear variable and divide it by 2. So we get -8. And then afterwards, we're going to square it, which would give us 64. Now that 64 should get added to both sides. Because when it gets added to both sides, I'm going to put a big equals there, we can now factor the y expression. Okay, so we can factor this. And that is a special factoring. So we would have x squared plus, well, it would factor into y minus 8 all squared. We could double check it, FOIL this out. It is what's above, and then equal to still 64. Now it's matching the form of a circle. So this is a circle with the center 0 and 8, and r equals, well, 8. So the square root of 64 is 8. Okay, so that's if they force us to. Again, I hope not. I think for now that's nothing that's too important. I would hope that this would be it. So because once you get the equation converted to just x's and y's, so no more r's and thetas, we did accomplish what they wanted. It's just maybe not in the best form yet. All right, so number 4. Okay, so number 4, we have r equals cotangent theta cosecant theta. Well, cotangent and cosecant we don't like, right? Let's change those. Cotangent is cosine of theta over sine of theta. And then cosecant of theta is 1 over sine of theta. All right, so we can simplify that right side. We have cosine of theta over sine. You know, we can write it as sine squared, but I'm actually going to just keep it as sine theta. Because right now I'm going to now say, well, let's cross multiply. Okay, so the 1 and that would multiply, which gives us r sine theta equals cosine theta. And then now it's similar to the last problem where I said, well, if I have a sine of theta and a cosine of theta, I want r's with them. I want it like those equations right there, the first two. Okay, so that means this I've got, this looks good. That r sine of theta, I know it's just y, but then I see a cosine of theta and sine of theta that are missing an r. Well, how about I just multiply both sides by r and squeeze them in. Okay, so that's a, let me erase that, let me fix that. So what I'm saying is we should just, so there was my, I'm gonna put it a little closer. Okay, so I'm saying I want an r with them, so I'm just gonna multiply both sides so that I get an r. And then now I can say, well, that in the blue is y. That in the purple, the first purple, is also y. And then on the right, that in the purple is x. And then we can say, oh, y times y is y squared equals x. And then that's fine. That's as good as that one gets. What that is a special type of parabola, is the parabola. But again, for now, that's all we want. Okay, so we did convert this one. So this one was actually looking maybe worse at the start because of cotangent and cosecant, but it changed into something not too bad. Okay, so that's our conversions. Okay, so converting between polar to rectangular, a little trickier. Now, and again, the first two, we could have used the 4 that are in this brace here. I chose to mix it up. And then similar, with number 3 and 4, we could have done a lot of weird substitutions and eventually gotten these answers. Okay, but that's it for now. Thank you for watching, and please let me know if you have any questions.